Okay, I'm going to share my other screen this time. I'll just share the whole screen. Now you're just seeing the one big slide, right?
Yep.
Okay, and you see my mouse right now?
Yes.
Okay, good. So, all right, so we're describing this binary antipodal signaling when we started off with the signal in a time domain, and now we're representing it as a vector. And note that, all right, we don't know what this E sub S is, it's some value, but that's that the absolute value is not important for this discussion. It will be relative to the value of noise, but the absolute value is not important. So we'll note that because k is equal to 1, a bit maps into a symbol on a one-to-one basis, and so we'll call this equality here, equivalence, that the energy in the symbol is equal to the energy in a bit. Now, strictly speaking, bits are kind of virtual concepts, right? And so defining energy is a little bit strange, but it again, it's a relative basis, and so it helps us if we can describe the amount of energy it takes for us to communicate one bit of information to the receiver within a given noise environment, then that's kind of like normalizing out all the whole transmitter and antenna and all those design issues, and normalizes all those factors out. So we can look at a particular type of signaling and say that we'll achieve a certain error rate if we have a certain amount of energy per bit versus our noise performance, right? And so that digital engineering, digital communications engineer can design the waveform and the signaling, and then the circuit and system designers can go and make that happen, right? So then they can set a certain amount of transmit power, a certain amount of antenna gain to make sure that at the receiver that you achieve an acceptable bit error rate or symbol error rate given the amount of distance between these things and the transmitter receiver and the type of noise that you expect to get, right? So it allows us to kind of divide up these engineering activities. All right, so let's look at now the decision area for symbol 1, right? So we're wanting to understand which, if we receive an R, how are we going to map that to a decision that produces the M equals 1, right? So so here we're taking those previous equations and we're taking the R times the S1 here, where we've gone ahead and replaced the E sub B for the E sub S, right? And now we recall that there's this dependency for the probability of that message being sent, the a priori probability, and subtracting this half of the energy of the bit, right? So this was our what we called our bias term, and we substituted in those values. Now, what we want is that to be greater than all the other alternatives, right? Well, this is just binary signaling, so there's only one other alternative that we have to consider, and that's this S of 2. So it would be R times S of S2, which is this minus root of ES or minus root of EB using a substitution, plus all this here. Now, this is a probability that this S2 symbol would be sent, would be needed to be sent, right? So it's the a priori probability, and so we have the 1 minus P, okay? Now just repeating that equation up there for context. So now we can simplify a bunch here by moving terms around and noting that these additions, subtractions of natural logarithms, we can pull those arguments inside as a quotient, right? So now we're just so all we're doing is canceling these E sub b's here and rearranging some terms here to end up with this relationship here. So now we'll just define that as a threshold. Okay, so we'll call this RTH, and then we'll create this drawing down here diagram. So here's our origin, or voltage equals 0 of this symbol, and here's S1. It's going to be have an amplitude of plus the root of E sub b, and S2 over here, right? So now this RTH here is going to be placed as a function of these probabilities here and scaled according to the amount of noise and the energy, or the relationship with that noise and the energy per bit. So how does this work here? If the probability of S2 being sent is higher or lower in this case? Than the probability of D1 here, right? Higher, yeah. So we're if the you can look at how a natural log behaves, but relative to 1, and where that's going to so where they would be equal probable, right? If P is equal to 1/2, they're equal probable, so you'd have 1 minus a half, so you'd have a half over a half, so that'd be 1, right? But if you think about it, if the probability of S2 being sent is 1, then we would know that S2 is the actual symbol being sent, right? Because if the probability S2 is 1, then that means probability S1 is 0. And we really don't have to do any work, right? Because we know for certain that S2 is the right one. So that D2 would then need to go from minus infinity to plus infinity, right? So that would mean this threshold is way up there. The conversely, if we were certain that S1 was the one being sent, if it was being sent with a probability of 1, then the probability of S2 would be 0, so we'd have a natural log of 0, and that would be basically minus infinity, right? So and the whole decision region would be D1. If again these are equal probable, then the threshold would show up here at 0. So it gives you a little bit of idea in that we can use the prior knowledge of the likelihood of which symbol is being sent to massage that decision area to ultimately minimize our error rates overall, right? So if it's more likely that S2 is being sent, then we should probably make that decision area a little bit larger to account for that, to weight it a little bit. All right, so error probability. What is the probability that impairments cause the received symbol to be estimated in the wrong decision area and therefore mapped to the wrong symbol, right? So we said, all right, these are decision areas, but what if we had so much noise here that even though we sent S1, it shows up over here, right? We're going to, according to this decision rule, we're going to map that to a D2, right? We didn't actually calculate D2 here, we calculated D1, but we know that if it didn't fall in D1, it must fall in D2 because this is a binary signaling type of thing, right? So, so what is the probability that in this case, simplified, that our additive white Gaussian noise would be so strong that it moves this constellation point down here, okay? And therefore, we're making a wrong conclusion about it. So we need to know the statistical nature of the random impairments. So we're going to assume additive white Gaussian noise, mostly because that's the easier one that we know. It's probably density function. If we're dealing with some nonlinear aspects or some other type of noise mechanism or interference mechanism, we would need to describe its PDF, and that might be quite challenging to ascertain what the PDF is of a particular interference signal. And also, as I mentioned a few times, you know, in kind of a practical way, you know, this is often going to be your limiting factor, right? So you can control a lot of things. You can kind of control your noise to a degree if you spend a lot of time and effort on developing a great low noise amplifier, but you're still going to be, you know, confronted with that no matter what. So so we're going to assume additive white Gaussian noise and study it with respect to noise power and the minimum distance between the constellation points. And as we know, we can kind of conclude that that is related to the overall signal power in an absolute sense, and the number of constellation points or the number of symbols, and the actual constellation design, right? So we looked at last lecture. Some constellations were kind of rectangular, some were polar oriented. In your homework, you're looking at kind of an oddly shaped 8 QAM type constellation, right? So all right, so let's again look at this antipodal signaling. We will look at, we have two different symbols that can be sent. So we really want to calculate the probability of error for both of those and then add them up, right? So, and this is basically describing, all right, so what is the idea that M is not equal to one of these, the particular M that we're examining in the particular term of this outer summation, right? And we're going to integrate this probability density function over these other decision areas, right? So in a more general case, that decision area might be described by hyperplanes. In this case, it's a more one-dimensional, it's along the real line, right? But this is describing over that overall area, right? So we're integrating this probability density function of R conditioned on what M was actually sent. Okay, so so this is the error, right? That we're going to have an R that lies in the wrong decision area. We need to look up all the different decision areas for all the different symbol correct symbols. Okay, so this is pretty generic, except with these twos here, we kind of implied that it's antipodal or binary. Okay, so now let's look at these terms individually, right? So there's this outer summation implies that there's a couple of terms here, and let's look at this. So we have this integration for D2 here, and where R, we're looking at R in the region of D2, where S is basically S sub 1, right? So it's this positive plus the root of E sub B, okay? And that's at a probability PM of P. Whereas let's look at decision, let's look at the other symbol S2, which is transmitted, this PM is 1 minus P, and the other decision areas would be D1, right? So here on this left side, the first term, we're looking at symbol 1 lying in correctly in decision area 2. In the second term, we're looking at the probability of sending a symbol 2, but it in the up in decision area 1. So these, both of these would represent an error. Okay, and now let's start describing our decision area. Okay, so this is decision area 2. So that's going from negative infinity all the way up to that threshold, right? That we defined as that mildly complex function of the logarithm ratio of the logarithms, the logarithm of the ratios, sorry. And then likewise over here, decision area 1 is going from that threshold out to positive infinity. So now we just need to integrate these things out, right? So we can describe this kind of in shorthand as this probability that this Gaussian distribution with this mean now this distribution is not zero mean. We're looking at it relative to this E sub B, right? That's where that transmitted signal would be centered, and its variance is described by this and not over 2. Okay, and that it would be less than that threshold, or or in this case, it would be greater than the threshold when we're looking at the distribution that's centered on the left-hand side. So if we look at this thing, this is the ideal symbol location, but there's going to be a distribution, a Gaussian distribution of noise centered around here. Now, if it's nice and narrow here, then that tail is going to be really small by the time it gets over here, right? But if we've got a lot of noise power relative to our energy, right? So energy is showing how far it is from zero, which impacts how far it is from the threshold. So energy is determining this separation. The variance of noise or the noise power is determining how broad that Gaussian distribution is. And what we're concerned with is the distribution here that is tail leaks out over here, right? So we know that Gaussian distribution, those tails go on forever. So there's a finite probability that the noise would push this symbol over here, right? Likewise, there's a finite probability, there's a Gaussian distribution centered at this energy or amplitude, and its tail is going to leak into this decision area and result in a error. Okay, broader the higher noise power, the broader that distribution, and the more area under this curve that we're integrating, we're going to have. Okay. So that's what we've described here in this equation. And now we can note that it's a good thing we looked at that Q function, because now we can write this in terms of the Q function, and we can look at those values, call this X, and we can draw this on a graph, and we can, if we know these probabilities, we can draw this probability error with respect to this combination of the energy and the noise. Okay. All right. So now if we just write that equation back up here at the top for context. So if we have an equal probable distribution, then the threshold is 0. So these terms go to 0, and that simplifies that in there. And of course, these p's now get simplified. We'll note that now if RTH is 0, then the arguments are the same. So we can just add up these. So that's 1/2. That's 1 minus 1/2 is 1/2. So they just sum to 1. So in the equal probable case for binary antipodal signaling, right, then our error rate at the symbol level, which since k is equal to 1, is equal to our error rate at the bit level, there's a 1-to-1 mapping there, is described by that. Okay, so any questions?
Wait, can you go back?
Sure.
I have a question.
Yeah.
When
Great.
when is this method used as opposed to like another method covered? What is it ideal for, I guess?
For the binary antipodal signaling?
Yes.
You're saying? Okay, so what we'll do is we'll look at other types of signaling schemes, right? Other levels of Comm or QPSK or that type of thing. And we can go through this same exercise. It's more complex signaling, so it's going to be a more complex exercise, but we'll do that same thing, and then we'll compare them. So what that ends up doing then is let's see if okay. What we'll see is that different constellations are going to have different performances, right? But there's a trade-off, right? If one was always better than the other, we wouldn't really need to worry about it. Okay, so you're seeing which this is actually lecture 6, but this is Tuesday's lecture, right? So now if we go find one of these constellations here, right? So we can look at this guy and say, wow, this is you know, this is 64 Comm, right? So that's mapping 6 bits into each symbol, right? So if our channel allows us to send 1,000,000 symbols per second, let's say, right? So its bandwidth is, you know, on the order of that, megahertz or 2 of bandwidth. Then I'm totally hand waving that right there. So then that's fixed depending upon how much bandwidth at the you know, spectrum level, at the RF level we're available to, right? So we can send 1,000,000 symbols per second. Well, here now for each symbol we're sending what did I say, 8 bits or 6 bits, 6 bits, right? 2 of the 6 is 64, I think, right? Yeah. So we're able to send 6 bits, but you're going to see when you do this, it's like, boy, your noise margin here is terrible, right? We see that here is like with this, we need a signal noise ratio of on the order of 22 dB. You know, 30 times the noise power, or was that maybe more than that? I don't know. My dB conversions are a little off there, but many times the signal power than a noise. So we need a lot of signal power to be able to achieve this separation. But if we do have that signal power, we can be very efficient at sending our bits across that spectrum. But if we have a different spectrum, then I mean, I'm sorry, we go to this antipodal signaling, then we're going to we have a much easier decision to make, right? So the distance between these guys is larger, but we're only able to send 1 bit for every symbol, right? So 6 times slower bit rate that we're able to achieve over that same channel, but we don't need near as much power. So in the end, we're going to see that this is basically as good as it gets. Okay, so this binary antipodal signaling is we can call this binary phase shift keying, where we have the same amplitude but opposite phase, right? So a difference of pi radians or 180 degrees of phase. So we'll call this a binary phase shift keying. From a symbol standpoint, that's as good as you're going to get, and everyone else is going to be worse than that. So so that's why we would do one versus the other. So you're looking as an engineer and you're designing that waveform, you're looking at, well, am I dealing with the super high power system in a very benign environment? Let's say, you know, I've got a Wi-Fi in my house. Yeah, I've got to maybe go through a few walls, and that's going to impact my received signal power. But yeah, I'm plugging the access point into a wall so I can push out a fair amount of power. That's limited by regulation, but I can achieve some pretty good signal noise ratios, right? So the amount of signal energy relative to the noise, and therefore I can go up to like 1024 QAM type signaling. So I'm getting 10 bits per symbol through. And also LTE will do adaptive bit loading, and it'll look at, for a particular user, relative, where they are relative to that base station. They may be real close to the base station and therefore have a great signal to noise ratio. The signal's really strong, or they may be way far away from the base station, and they're at the very edge, and so the signal is very weak. It's dissipated in the propagation, and so you change the modulation depth. You change whether it's BPSK or QAM or 16 QAM or 1024 QAM type of thing. So and that changes your data rate, your effective data rate. So that's why if you're real close to a cell, you might be able to watch your online video without any hiccups. But if you're far away from the cell, you might be downgraded in terms of the quality of the video being sent out. So it's compressed more in order to fit it over the available channel. So did I over explain that enough? So let's look at then the homework assignment now. So I think I gave you some hints on these others, but I skipped over this number 2 because we really needed well, certainly needed Q functions, but also this lecture here, I think, gives you the insight you're going to need to set this problem up. So think about how this relates, right? So you've got Gaussian random variable, mean is 0, but it has a certain variance of 10 to the minus 8th. So now you're looking at the probability of the value of noise exceeds 10 to the minus 4th, right? So now you set those integration limits up accordingly, right? Where this is the noise, what is its, if it's 0 mean, what's its probability that it exceeds that, right? So we're going to integrate from here, this value up to infinity, and look at that area under that tail of the curve. And then these different aspects here are really just setting up different limits, and use the Q function and look it up in that table in this PowerPoint or PDF that I uploaded, and that should get you the answers on all these homeworks, as in the test. It's most important that you set the problem up and describe it to me, how you're setting it up, so that we can give you as much credit as possible for understanding the concepts and not losing all your points because of some mathematical calculator fumble or something like that, right? So okay, so yeah, let's make the homework due Monday evening, and I'll still think about it. I need to do a little course planning, but test either a week from Friday or the following Tuesday, with a little bit of preference for the following Tuesday. But want to make sure that if we delay too long, then we're testing you over too much, right? And I'd rather test you over a smaller part, and then equivalent on the next midterm exam and stuff. So I'll plan out the exam a little bit, and but regardless, we'll go over in the class period beforehand what the nature of the problems will be, and so you can kind of focus on those type of things. I know we're covering a lot of material. A lot of it is hopefully review, but probably going a little bit deeper than you had in your previous probability and statistics classes and stuff. So, all right. Any other questions?
Professor, can you scroll down to number 5?
Number 5 on the homework. Yeah. Go and share that again. Come on, where's my cursor? There it is. Okay. All right, number 5. Yeah. So
Do you want the distance to be 2a or a? Because in the problem it says 2a, but in the
oh yeah. Okay, I'm sorry. Yeah, good point. Let's make those 2 A's there. Sorry.
Okay.
That'll I mean it's all relative, but this will make it easier on the grader. So yeah, so you know, here you're and I hope I've drawn these things reasonably well. If you have access to the book or the PDF of the book, it's in there. I'm not exactly sure which one it is, but yeah, so you're going to look at the energy of each one of these relative to these A's, and you know, these A's from this, you should be able to figure out what the distance is from the origin for each one of these, right? So in these cases, it's pretty easy. In these others, these corner cases, you just need to use a little Pythagorean theorem or whatever it is, and stuff. So add them all up, and then see which one consumes more power, right? So okay. All right. Have a great weekend. I think we're at time. So take care.
Thank you, President. Thank you.